Welcome back. In this screencast, we take the result that the sum of the measures of the angles of a triangle is 180 degrees, and we expand that result to polygons in general. For example, that's a polygon. And what if we want to know what all of its angles add up to? It will be rather difficult for us to construct parallel lines, and parallel to what? So maybe we go at it a different way. And the thought is that because we have all this space here and there are no triangles in the space, but we know something about triangles, we can just pick our favorite vertex and break the hexagon into triangles. And so each of those triangles have angles that add up to 180 degrees. And because we started from this vertex right here, every part of every interior angle of every small triangle is also a part of an interior angle of the hexagon. There's no funny triangles or shapes trapped inside. Every part of every interior angle of every triangle is a part of an interior angle of the hexagon. And so the sum of the measures of the angles of a hexagon is 4 times 180, that's 720 degrees. And you're thinking, well, that's a clever argument. Can we do that with something else? Well, sure, that's an octagon. So we pick our favorite vertex. It can be any of the vertexes, which we would call vertices. We can just make the same kind of argument. We go from one vertex all the way around. We draw all of the diagonals from one vertex, and each of these has interior angles that add up to 180 degrees. And so the sum of the measures of the angles of this octagon is 1, 2, 3, 4, 5, 6 times 180, and that's 1080 degrees. So now I know what you're thinking. You're thinking, wait a minute, is there a pattern? And the answer is, sure there's a pattern. What happens for a generic n-gon? Well, the sum of the measures of the interior angles is, where did this 4 come from? Where did this 6 come from? The 4 was the number of triangles we could generate by drawing diagonals from this point right here. Well, we drew 3 diagonals, and that divided things into 4 triangles. We drew 5 diagonals in the octagon, and that created 6 triangles. When we have an n-gon, we draw n minus 2. No, we draw n minus 3 diagonals. That seems about right. We draw n minus 3 diagonals. That makes one more than that, n minus 2 triangles. 6 minus 2 is 4. 8 minus 2 is 6. So we have n minus 2 triangles, and each of those triangles has an angle sum of 180 degrees. So generally speaking, this is the sum of the measures of the angles, interior angles of an n-gon. In both of the cases that I drew here, these are regular n-gons, and so we can figure out what each one individually is by taking the sum and dividing by n. We weren't asked to do that here. I will consider the other question. And the other question is, yeah, okay, fine, we can talk about the interior angles, but we can also draw exterior angles at every vertex. And if we draw exterior angles at every vertex, what do those add up to? And that's a really good question. At this vertex, we have an interior angle, call it I1, and an exterior angle, call it E1. And we can do that all the way around. The interior angles are I2, I3, I4, and I5, and the exterior angles are E2, E3, E4, E5. And then we note a couple of things. We note that these add up to 180 because they're supplementary. These add up to 180 because they're supplementary, and so on around. So I1 plus up to I5 plus E1 up to E5. That's just adding all 10 things that you see. That's 180, that's 180, that's 180, that's 180, that's 180. That's 5 times 180 degrees. Well, what is that? What do we have to do with that? Well, we know what this is. This is 5 minus 2 times 180 degrees. And this is the sum of the exterior angles, some of the measures of the exterior angles, and this is 5 times 180 degrees. So when we want the sum of the measures of the exterior angles, that's 5 times 180, that's 3 times 180, leaves you with 2 times 180, that's 360 degrees. So if you add up all of the measures of the exterior angles of a pentagon, you get 360 degrees. Now, here's the curious thing. There's nothing special about this being a pentagon. This will always be n times 180. This will always be n minus 2 times 180. And so this will always be 2 times 180. So it does not matter that this is a pentagon. It could have been a hexagon or an octagon or a decagon, and it does not matter. The sum of the measures of the exterior angles of any polygon is 360 degrees. So while this result depends on n, this result does not depend on n. This result is different depending on the shape. This result is not different depending on the shape. Okay. I hope that this is helpful to you, that it has given you information that you can take with you, maybe made what was read in the textbook a little bit easier to digest. We'll see you in class. Can't wait.